Greetings, physicists. My name is Greg, and today I'm going to show you guys a very interesting textbook from my library. This is Mathematical Physics, A Modern Introduction to Its Foundations by Sadri Hassani. It is in its second edition and was published by Springer in the year 2013. And out of all of the textbooks that I own, this one is probably the most insane, and you'll see why in just a moment. So the first thing you'll notice about this book is that it is thick. This is one thick textbook. It is over 1,000 pages of pure mathematics. You could definitely put this in a sack and kill someone with it if you wanted to, although I would not recommend it. So this book is a graduate level textbook and is mostly designed for physicists to learn all sorts of different mathematical techniques which they can then use in their research. So a lot of the math you'll see in this book you will not see in undergrad. This contains a lot of stuff like group theory, Green's functions, a lot of linear algebra and Lie algebras, Clifford algebras, things like that. All sorts of different type of algebras. But yeah, so let's take a look at the back of this book and see what it's really about. So, the goal of this book is to expose the reader to the indispensable role that mathematics, often very abstract, plays in modern physics. And abstract is right. This is very intense, definitely. So, without further ado, let's open this book up and see what it's all about. So, there's the title page, Mathematical Physics. According to the copyright information, the first edition was published in 1999, the second edition in 2013. So there's the preface to the second edition. And I really like this first sentence from the preface to the first edition. It says, "It is said that mathematics is the language of nature. If so, then physics is its poetry." Now, I don't know about you, but I think that's really beautiful. I really like it whenever textbooks get all artsy fartsy and stuff like that and get, they get kind of like deep like that. But that's really why I like physics, honestly, is, yeah, if mathematics is the language of nature, then physics is its poetry. It's like doing poetry in a ways. But one thing I like about the preface is that it's kind of broken up into different sections. So this talks about the philosophy of the book, and it talks about how it's basically for both physicists and also mathematicians that are interested in physics. And it talks about all sorts of features. So it says it has over 350 worked out examples and over 850 problems, which is a ton. That is a lot of problems. So if you really want to polish up your advanced mathematics, this is the book to go. And it talks about the organization and the topic coverage and the acknowledgments, and these are all the different textbooks that helped contribute to it, which I think that's kind of cool. I mean, it's like, no textbook is written in a vacuum. Even textbooks need textbooks to help them out. So, and yeah, Sadri Hassani from the Department of Physics at Illinois State University. So, note to the reader, mathematics and physics are like the game of chess, or for that matter, like any game, you will learn only by playing them. No matter reading about the game will make you a master. Again, another very good quote, but very true. If you want to improve in physics in any sort of way, you got to know how to play the game. And the only way to know how to play the game is by, well, sitting down and actually playing it. So here's the table of contents, and you're going to see some really wild stuff in this book. Some very, like I said, intense mathematics. So it starts off with an introduction to like math, the fundamentals, sets and things like that. Pretty standard. Set theory is, the fundamentals of mathematics basically. So it's pretty standard to start off a textbook like that. And then you've got finite dimensional vector spaces and algebras, which is basically like your linear algebra, things like that. This teaches you how to, what an inner product is and things like that. This is what, vector spaces are. And then we get into operator algebra. It tells you what operators are, how they work, what a Hermitian operator is, what a unitary operator is, stuff that's very useful for obviously quantum mechanics. And then it has matrices. This teaches you change of basis, what an orthonormal basis is, and then how to like manipulate matrices, like take a determinant, things like that. And then we have spectral decomposition, and then we get into Hilbert spaces and classical orthogonal polynomials. So things like Legendre polynomials. We have Hermite polynomials. Very powerful stuff. And then, of course, Fourier analysis. It can't be a math methods textbook without Fourier analysis. And then we get into complex analysis. So a lot of this stuff is pretty standard for a math methods course. As a matter of fact, this textbook was actually the book that I used for my graduate level math methods course. Let's see, we got all the way up to complex analysis, and I think we got to about chapter 12, where it starts talking about multi-valued functions and the residue theorem, things like that. We briefly touched into differential equations, and we did talk about calculus of variations, which is somewhere in here. Yeah, there it is. But this was like kind of as an aside, basically, at the start of the semester. But yeah, then it gets into some really intense stuff. Differential equations is obviously extremely important. Basically, all of physics. You know, you're going to see that in whatever, whether it's classical mechanics, whether it's uh, electrodynamics, you know, the thermo, obviously, with the heat equation. You're going to see all sorts. Differential equations are everywhere, not even just in physics, but in like biology and chemistry, things like that. So then we got operators in a Hilbert space, very useful for quantum mechanics. And then we have Green's functions, the infamous Green's functions. I think this part with the Dirichlet, I think is how you pronounce that, the Dirichlet boundary conditions and the Newman boundary conditions, I think that's literally like from the first chapter of Jackson. So some pretty interesting stuff right there. And then we get into the really crazy stuff like group theory, which is extremely intense. We did not get this far. So you got group theory, and then tensors and manifolds, extremely useful in general relativity. And we have Clifford algebras, analysis of tensors, and then we get into Lie algebras and all sorts of fun stuff with that. And then we get into fiber bundles, which I don't know why the hell I'd ever need to know about fiber bundles. But I guess maybe it has something to do with general relativity or something. I don't know. Very strange. But if you know what fiber bundles are used in physics, please let me know in the comments. And yeah, we have then gauge theory and then differential geometry and Riemannian geometry, which is obviously, yeah, there it is, general theory of relativity. So some very, very intense mathematics, extremely intense. And you'll see it's even crazier when we get into the actual text itself. So then I think this is kind of cool. It shows off a list of all of the very important symbols in the text. So if you ever see a symbol you don't know what it is, you can basically go to this part and it will just tell you what that symbol means. So I don't know if this is very useful or not, since it is literally every symbol in the book, but it's kind of cool that they have it. And I do like that it's sorted by topic, so that makes it a little easier. And now we get into the actual text itself. So I'm just going to be flipping around. So yeah, as you can see, it has all sorts of really cool examples. This is about linear functionals. Let's see, and then we get into, yeah, all sorts of really neat stuff. And then it also tells you a little bit about the people. I think this is kind of cool. It tells you a little bit about the people behind these discoveries. Every once in a while, you'll see these historical notes where it'll tell you, give you a little bit of a biography about the individual. So this is obviously Legendre polynomials, and obviously it's talking about Legendre, which is pretty cool. So yeah, it's, as you can see, it's very dense, extremely dense. Uh, this is a fun problem with the you have voltage on an upper hemisphere, and then you have the same voltage but negative on the lower hemisphere, and you got to find the potential outside of the hemisphere, and you solve Laplace's equations, but then you got to use Legendre polynomials to get it for the boundary conditions. I think this was actually a test problem one time. I might do this problem in a future video because it's really fun. But yeah, it is just, yeah, there's the Fourier analysis. You can decompose basically any function as a sum of sines and cosines. So a lot of really cool stuff. And like I said, it's just so what's so insane about it to me is that it's so big and so dense. Like, this is intense. It is an intense book. If there's anything you wanted to learn about in math or in regards to physics, it's probably in this book. Obviously not the super specialized stuff, but yeah, this is a very well-rounded text. It's it's honestly a little intimidating, if I'm going to be honest, and it mostly is just pure mathematics, which is if you're a physicist like me, can be a little scary. So when I took my math methods course, let's see, we did a part one, which was just linear algebra, and then we got all the way to Hilbert spaces. We did operators, and then yeah, we did the orthogonal polynomials and Fourier analysis. And then, like I said, we got through chapter 12, and then we touched a little bit on differential equations, specifically, I think Laplace's equation in spherical coordinates. And then we did a little calculus of variations, but that's basically it. So this textbook really does show just the pure extent of the math that's required to do this super advanced physics. And it's just some very, very cool stuff. The textbook itself is also really good quality. Like, the binding is really nice and firm, and the pages, they're firm, but they don't feel fragile at all. It doesn't feel like I'm at risk of tearing them at all. So here's kind of a chapter on group theory. And this Galois fellow seems pretty interesting. He was only 21 when he died. I'm literally older than he was when he died. And it also says here that he was arrested several times for his agitations, although he continued to work on mathematics while in custody. And then it says that he was killed uh, after a duel, and that his funeral 3 days later sparked riots that raged through Paris. So it seems like this dude was like the King Von of his day or something.
Bro, he was dead, bro. If he wanted you out of there, he'll go do it himself on feet.
No, yeah, here's a section on spinners. Uh, very cool stuff. A lot of like really advanced mathematics, obviously. But that's probably what makes this book so insane, is that there's just so many different fields that it covers, and it covers each of them in a ton of detail, and it's very, very dense. Each section is. So this is a really great book for reference. So that was Mathematical Physics by Sadri Hassani. It's a really great textbook. I'd recommend this to grad students, both physics grad students and math grad students that are interested in some of the more physical applications of the stuff they're learning. I wouldn't really recommend this textbook to anybody else just because it's so intensive, but I would recommend this book to undergrads, maybe if they want to learn a bit about what they'll be doing in grad school, or maybe want to learn some of the more fundamental mathematics of the stuff that they're learning in their courses. So yeah, it's a really great reference material. But that has been this video. I think I might make a series out of this where I talk about different textbooks in my collection. If you're interested in that, please like the video and comment down below. And thank you so much for watching. Have a great day.